Well, if you're not string theorists and you're not cosmologists, then what the hell are you? Quantum computer? People wandered in here by accident? What I want to talk about is cosmology. There's a lot of ideas out about cosmology. Most of them are sort of random, undisciplined ideas, which I'm rather certain I'm not going to go anywhere. When I do physics, I like to try to apply some discipline to it. The discipline that I try to apply to it, I'm not always successful, comes from experiment, observation, and principles. Principles such as the second law of thermodynamics. You'd be amazed how many papers there are out there by well-known physicists doing cosmology who are perfectly happy, although they sometimes don't realize it, to violate the second law of thermodynamics. That's not something you really want to violate with impunity. I mean, you may be forced to it. You may come to some situation where circumstances actually force you to think of violating truly fundamental principles, or clashes of principles happen. But I think one should be careful about violating principles all over the place. I'm going to tell you what I think. This is my view of what the things which the guiding stars, which I think should be guiding, if not you, at least me, in thinking about cosmology. I'm going to write them down, and then, incidentally, this is the first I understand of 2 lectures. The second lecture will be on the holographic principle and how it's applied to cosmology, or how I would hope that it will be applied to cosmology. Today, I'm only going to mention it as one of the guiding stars, but let me write down a list of things which I think are important and which I think one doesn't want to violate. The first thing, now, you could question all of these things. All of these things can be questioned. There's no question about it that they can be questioned, but let me write them down anyway, since I am inclined to believe them at the moment rather strongly. The first is the success of inflation. Now, there are some people who think that inflation is still a guess, and I suppose it is, but it seems to work awfully well, and so I will take it as a given that slow roll inflation, conventional slow roll inflation was a part of our history in the early universe, as understood in the standard, in what's called the standard model of cosmology. So slow roll inflation, I think, is one of the key guiding stars. The second one is the existence of a cosmological constant, lambda. Lambda, very, very small, of order 10 to the minus 120 in natural units. At the moment, that seems to be a fact. It doesn't seem to want to go away. The more observation that's done, the more it looks like a cosmological constant. And I take it as a given that there is a cosmological constant in nature which is fine-tuned to 1 part in 10 to the 120. The next thing, now this will appeal to string theorists. It may not appeal to other people. I don't consider myself a string theorist, but I do consider myself as being on board a certain view of the vacuum structure of, let us call it quantum gravity, or let us call it string theory, or let us call it cosmology, or whatever. And it's the thing that's come to be known as the existence of a landscape. A landscape of vacua, which may have as many or more than 10 to the 500 metastable vacuums. I think it's become a matter of conviction by now that at least among string theorists that vacuums with positive cosmological constant are at best metastable. And the reason is that we know with certainty, at least, that there are vacuums with negative cosmological constant and vacuums with zero cosmological constant. And it's rather difficult to understand how a vacuum with positive cosmological constant, positive vacuum energy, can be absolutely stable. So this is one of my guiding stars. Next, some things that came out of black hole physics. I'll call one of them, I will call observer complementarity, and I mean something very simple by it, which we'll come to in a moment. I'll explain what all these things, I'll explain what all of these things mean. You know what most of them mean. Observer complementarity. I'll come back to it. And the final thing is the holographic principle, which I will also explain in a moment. It is my view, and I don't seem to represent a very large number of people, but it is my view that this collection of things leads definitively to a view of cosmology which I think has been underrepresented in the literature, and I think which is very, very compelling, a very compelling consequence of these things. It's not a view of cosmology which is a complete view of cosmology in the sense that it goes all the way back to the very, very beginning, whatever that means. It's a view of cosmology which may allow us, hopefully will allow us, to push a little bit further back. Not back to the ultimate whatever. I suppose people like to think about a singularity. I have no idea if there was a singularity, and neither does anybody else. I have no idea how the universe originally began, but we have some ideas from here about where it may have been, or what it may have been, just before the time that we have access to, and that's what I'd like to talk about. All right, let me take these one at a time, but not necessarily in the order that they're there. Observer complementarity is the same thing as what I called last time when I was lecturing here, black hole complementarity. But since almost nobody was here, let me just say what it is. It's the basic idea that the description of physics outside a horizon of a black hole is complete. It's complete if we have a black hole that's been formed by some collapse of a star or anything else. Then there's the exterior of the black hole. There's the interior of the black hole. And one might think that in order to have a complete description of physics in the space-time, you would want to talk about slices through the space-time which cover both the interior of the black hole and the exterior of the black hole. From experience in trying to understand correctly how information works, how quantum mechanics works in the vicinity of a black hole, we've come to the following understanding. The following understanding is that physics on the outside of a black hole is absolutely complete, meaning to say that a complete quantum description of everything that made up the black hole, that may have fallen into the black hole, is eventually encoded in the details of an S matrix whose final state is simply the Hawking radiation. That no information is ever lost behind the black hole horizon, and or I'm going to take that to mean that no information is ever lost behind any kind of horizon, any kind of event horizon, and that whatever does fall behind the horizon is, or the description of things behind the horizon is a redundant description of which the same things are encoded in the Hawking radiation. The Hawking radiation and things behind the horizon are the same thing. They're the same thing in a different representation, in complementary representations. And by now, I think at least a large fraction of the physics community will buy into that, large fraction or a fraction theoretical physics community, in particular string theorists, will buy into that. And they'll buy into it largely because of the work on the duality between quantum field theory and quantum gravity as represented by the next thing, which is the holographic principle. All right, so observer complementarity, let me take it to mean the following. That if you take a point in the remote future, let's call it the asymptotic limit of the observer, or some observer who is characterized by a final evolution, a final point in the remote future. If you look at the backward light cone, and you look at everything within the backward causal, sometimes called a causal diamond, in the backward causal diamond of a point in the remote future, then physics in that region there is complete, and it has no need ever to discuss things behind event horizons. That's what I will mean by observer complementarity. And we can ignore what's here for most purposes, although it may be a complementary description of what's here. Okay, so that's that idea. The holographic principle is really just a way of combining the second law of thermodynamics with some gravitational ideas. How do we do this? I forgot how this works. Just up? Yeah, just up, okay. But I remembered some problem. Oh yes, the problem is that I can't reach the, no I can't. I think I've grown in the last few months. All right. Next is the holographic principle. Okay. The holographic principle is all about entropy and information. I'm not going to spell the whole thing out. And it has to do with the maximum entropy of a system, of a closed system, of an isolated system, of a region of space. So let's just go through the meaning of that again, because I'm going to use it not so much this time, but next time. The holographic principle says, supposing you have a region of space, how many degrees of freedom does it take to describe that region? It's equivalent to the question of what the maximum entropy that can be stored in a region of space is. Entropy is just information, but it's information that you may not bother measuring, but it is the maximum entropy of a system is the maximum amount of information that you can store in that region. And let me give you a qualitative definition of it, is that the entropy, first of all, the entropy of a system is not just a function of the system, it's a function of the system and your state of knowledge of the system. You say, supposing I know this or that about the system, you define an ensemble. An ensemble can be a probability distribution, or it can just be a specification of some subset of states of the system. Then, roughly speaking, or almost exactly, but you need a slightly more exact definition if you want to be truly precise, but this is very close. The entropy is simply the logarithm of the number of quantum states that satisfy whatever it is you think you know about the system, and so it's the logarithm of the number of states that are included in the ensemble. And the ensemble of states that represent your known amount of information. Now, as I said, that's a somewhat subjective idea because it depends on how much you think you know about the system, but there's a concept which is more robust, and it's the maximum entropy of a system. The maximum entropy of a system, it may be infinite. For most systems, it really is infinite. But the maximum entropy of a system is the logarithm of the entire dimension of the Hilbert space. In other words, the logarithm of the total number of states, the total number of orthonormal states that describe the system. And so we can just call that log of n, where n is the dimensionality of the Hilbert space. That's the most entropy that you can ever have in a system. And you can also think of it as the most amount of information that a system can store. It's also a measure of the number of degrees of freedom of a system. So let me give you an example. If you had, it used to be thought that the right way to do quantum gravity was to divide the world or a region of space up into little Planckian cells. We call them voxels, V-O-X-E-L-S. That's a word. Voxel is not an animal. It's It's the analog of a pixel, except a volume pixel. We divide space up into little cells, a large number of them. How many? Well, that depends on what you happen to believe, but I think until fairly recently, most people would have said divide space up into Planck-sized cells, cells of volume of Planck cubed. And now in each cell, a simple version of keeping track of information might be that in each of the cells, you can have a bit of information. A bit of information, and I don't know how many cells we would have to divide the world up into to have enough information to describe a region of space. But we might try to describe physics by simply the question of yes or no, is there a particle or a bit in each one of these cells? Yes or no. And if that were the right way to describe physics, then we would say the maximum entropy of the system was, well, first of all, the dimension of the Hilbert space, n, would be 2 to the number of cells, and the number of cells would be the volume of the system divided by the volume of each little cell, volume divided by basic volume, and then we would argue that the maximum entropy, S max, was just equal to V over L Planck cubed. In other words, the number of Planckian cells times the log of 2. Log of not S, log of 2. The most interesting thing about that is, first of all, that it's proportional to the number of basic degrees of freedom, the number of yes-no questions that it takes to describe a region of space on the one hand, and the other hand is proportional to the volume. Okay, I think we know with certainty that that's, they call this the voxelated world. The voxelated world broken up into a system of cells, each of which has a volume. All right, we know that this is a tremendously large overcounting of the number of independent states of a system, of a region of space, and the argument goes through black holes. So let me just, for most of you, I presume, remind you of the argument. For those who don't know the argument, let me just say it. Supposing you have a region of space. I'm going to draw a space-time diagram. Suppose you have a region of space, vertical is time, and here's my region of space, which I will take to be a spherical region of space for simplicity. And I have a whole bunch of particles in there passing through that region of space. What's the maximum entropy that you can have in that region? The argument is simply an argument of black hole physics together with the second law of thermodynamics. Let me just spell it out in detail. First of all, if all of the particles and all the structure is contained within some area A, then the object in there has to have less mass than a black hole, which would just fill that region. If it had more mass, it would overflow the region. It would certainly overflow the region. So it certainly has to have a mass less than the mass that would be a black hole that just fills that region. All right? Now, let's collapse a shell of matter around it, a spherical shell of matter. It could be a light-like shell of matter coming in, which just happens to have exactly the right amount of mass to create a black hole whose horizon is exactly as big as that region of space. This can always be done. Every relativist will agree on that. As long as there's less mass in there than a black hole, we can always throw in just the amount of mass to create a black hole whose horizon is exactly that big. The whole space-time figure would look something like this. The horizon would form at a point in the past over here, and then proceed vertically upward like that. And if you follow light rays, you would find light rays that originated over here would be bent when they pass the light-like shell. They get bent upward. Upward means that the expansion of the light ray, the expansion of the pencil of the group of light rays decreases. If you were to send out a light ray from over here, incidentally, the singularity over here, if you sent out a light ray from over here, the light ray would pass through the shell, but then get kicked backward by the shell and get kicked into the singularity. And it's right at this point over here where the light ray will get sent vertically upward, meaning that that light ray is no longer expanding, that the light ray is no longer spreading. Okay, that is the horizon of the black hole. And the horizon of the black hole has an entropy S, which is equal to its area divided by 4g h bar. And so we've taken a region of space, we've done something to it, we've taken an isolated region of space with a certain entropy in it, we've thrown something in, and we've created a system whose known entropy is the area over 4g h bar. It follows that the entropy that was in there to begin with is less than the area divided by 4g h bar. That's the second law. If you violate that, you violate the second law. So the conclusion is that the maximum entropy that you can ever have in a region of space is the area measured in Planck units. In other words, the world is not a voxelated world, it's a pixelated world, meaning to say that the maximum number of degrees of freedom that it would take to describe a region of space cannot be more than the area measured in Planck units. Now, this holographic principle, which I can no longer reach, yes I can, the holographic principle has been very well established by string theorists working in anti-de Sitter space. So I just very briefly at the moment want to remind you what anti-de Sitter space is. This will come up over and over again. But let me just be very brief about it right now. I'm going to show you what anti-de Sitter space is by showing you a figure here. Now, what do I have to press again? I forgot now. Somebody told me. Function F4. It doesn't work, does it?
Yes.
What happened? Well, now where is the picture? Oh, is it just a booting up? Press any key. Here it is. All right. That of course is a drawing of Escher's, but it is a very faithful and accurate drawing of several things. First of all, it's a faithful and accurate drawing of a spatial slice through anti-de Sitter space. Anti-de Sitter space is infinite in spatial extent, but it's negatively curved. And if you think of each angel and devil as the same size as every other one, you could also think of them as galaxies or anything you want, that would be a faithful representation of a space-like section through anti-de Sitter space. The holographic principle has been established for anti-de Sitter space with the following current understanding: that all physics inside the bulk of anti-de Sitter space is completely described by a quantum field theory, a conformal quantum field theory that lives completely on the boundary, that has no degrees of freedom in the bulk at all, has all of its degrees of freedom on the boundary, and furthermore, the number of degrees of freedom on the boundary, if you regulate the theory by moving in slightly away from the boundary, where the size of the angels and devils is finite, you regulate the theory both from the point of view of the quantum field theory on the boundary, and also from the point of view of an infrared regulator in the volume of the system, by just regulating the boundary, moving away a little bit from the boundary. If one does that and counts the number of degrees of freedom of the conformal field theory which describes the anti-de Sitter space, lo and behold, you find it's essentially 1 per Planck area. And so there's a strong piece of evidence that this idea of the holographic principle is correct. We're going to come back to that. I will tell you 2 more things that this diagram represents. It also represents Euclidean anti-de Sitter space, not a space-like section of it, but in higher dimensions, 1 higher dimension. It also represents the Euclidean section through anti-de Sitter space. But for my purposes, the really interesting thing that it represents is a spatial slice through open Friedman-Robertson-Walker cosmology. In other words, a space-like slice through open FRW cosmology is exactly the same as Euclidean anti-de Sitter space in the same number of dimensions. If we're talking about three-dimensional space, then a space-like slice through an open FRW universe is described by three-dimensional Euclidean anti-de Sitter space. That's going to come up, as you might guess. I'm going to suggest that cosmology in an open FRW universe is described by some kind of quantum field theory on the spatial boundary of it. But that's for next time. That's not for now. So we've gotten through two of these things. Let's talk about the landscape next. Well, the other three can all be described by one picture. Here's the picture. This is a cartoon of all of cosmology. Well, maybe we should add a little bit to the cartoon, maybe some more hills and valleys. The landscape is, of course, the space of scalar fields in string theory, and or space of vacuums, space of minima, and I'm interested only in those minima for today which have positive vacuum energy. And we suspect, I shouldn't say we know, we suspect that there's an enormous number of them. More than 10 to the 500 for sure. How many, nobody really knows for sure. All of them are metastable because you can decay from one to another. This ramp down here, this plateau down here, that is where ordinary slow roll inflation takes place. Most of these valleys here probably have rather large cosmological constant. The people who study the landscape and so forth would say most of it is filled with cosmological constants which are far, far too big to live in, order some fraction of the Planck scale. Down here is where we live, and we live in a vacuum whose vacuum energy is 10 to the minus 120. I'm going to ignore that for the most part today, the vacuum energy in here. And what inflation tells us is that for odd reasons that we don't really know, that we originated, or at least spent some time, our universe slowly rolling down a ramp here, where this ramp is also extremely fine-tuned. How fine-tuned? Not 10 to the minus 120, but the vacuum energy in natural units during slow roll inflation was at least 10 to the minus 14. When I say at least 10 to the minus 14, I don't mean it's bigger than 10 to the minus 14. I mean it's smaller than 10 to the minus 14. And so it would take a great deal of fine-tuning. It would also take a great deal of fine-tuning to make a potential in a field theory which looks anything like this. We'll come to why that, first the empirical reasons and then the theoretical reasons why such a thing might exist. All right, this is cosmology in a nutshell. All of it, basically, that we know about. Even more than we know about.
How do you get the number of 10 to the minus 14? What is this scale? Is a kind of a scale?
10 to the minus, where does 10 to the minus 14 come from? Observational cosmology. We could talk about it, but it's a standard observational cosmology fact. It's equivalent to the statement that what's usually called the scale of inflation is at least smaller than 10 to the minus 3.5 in Planck units, but the vacuum energy is the fourth power of that. You could not make the scale of inflation larger than that. So I wasn't going to talk about the details of observational cosmology. We can come back to it in question session or something. But that's the expected height, smaller than that. Right? All right. So this is more than all that's known about cosmology. The standard model of cosmology begins with a universe which is somewhere over here, slow rolls down to here, during which time fluctuations are created, and then reheating happens over here, and we fall down to our vacuum, and most everything that's interesting happened either in the fall down here or down at the bottom. So that's cosmology in a nutshell, if you like. Now, if the picture of the landscape is correct, it seems absolutely crazy to start the world over here. I don't know how the world started. But if we propose, for example, that the universe originated in some kind of very high energy event, Planckian event, an event which may or may not be a singularity, but which has far more energy than this 10 to the minus 14, it probably means we started way up high somewheres. If we started way up high somewheres, the most likely thing to happen is not that we will just smoothly roll down to here. That would be like throwing a bowling ball from the top of Mount Everest and hoping to hit the sea without getting stuck in a hole. Not likely. So anybody who would think a little bit about starting up high on a potential here would expect that in a fairly short amount of time, you're going to get stuck in a minimum. You get stuck in a minimum, you start to inflate. Not slow roll inflation, but just inflation at this minimum. You sit there for a while and you tunnel. You tunnel to some lower minimum. Right? You tunnel and then perhaps get stuck in a neighboring one. A series of tunnelings to the vacuum just before our home. That's the only one that can possibly have any interest to us today. All of this stuff is probably diluted away vastly. Even this is very likely diluted away to where we can never see it by the slow roll inflation over here. But we're going to ask the question, is it possible that we can see and learn anything about this vacuum here? I call that the ancestor vacuum. The ancestor vacuum, the one just before we tunneled out onto this plateau. We tunneled out onto that plateau, rolled down, started some slow roll inflation, and then got trapped in our minimum. That's the picture of cosmology that I want to advocate. It's the only one that I see making very much sense. But one of the puzzles is why this incredible amount of fine-tuning, and it is an incredible amount. We'll estimate it in a little while how much fine-tuning takes place. Now, this picture of a series of events is probably not really the right picture. The right picture is probably, you can think of this as a picture in series. I want to talk first about a picture which is in parallel versus series, in the same sense as circuits can be in parallel, or circuit elements can be added in parallel or series. That's clearly a series of events. Parallel events are things which are taking place in some sense simultaneously. All right, let me start with the universe up there at the bottom of one of these holes. It's going to inflate, and it's going to create something, at least locally, that looks like a de Sitter space. A de Sitter space has a causal structure, a conformal diagram, which has a time-like infinity, t equals infinity, which is itself a space-like surface, and the Sitter space is just the region below that horizontal line. This is not a global picture of the Sitter space, it's just a piece of the Sitter space over here. The metric exponentially increases. The metric in the space, it's conformal to just this half plane here, but the metric blows up very quickly as you approach here, and so there's an enormous amount of space-time volume near t equals infinity. That's the exponential growth of the Sitter space. And there's an infinite amount of time from any point, any finite point, to a point at t equals infinity. That's the conformal structure of the Sitter space. And the Sitter space is the sort of space that you would get if you sat in one of these minima forever and ever. Now, you don't sit in the minimum forever and ever. These spaces are metastable. They're metastable because they're metastable, because they're not absolute minima. So what happens? Well, the whole space, which has inflated enormously, doesn't simultaneously go plop to the next minimum. That would violate causality. What happens is quite different. What happens is that bubbles nucleate. Bubbles nucleate and expand with essentially the speed of light. They expand with the speed of light, and the bubbles are simply bubbles of the next vacuum down. Now, the vacuums are not really ordered in sequence. There are a highly multidimensional space of them, and so it's not necessary that you decay to any one particular vacuum. You may decay to a whole bunch of different vacuums. You may have a decay over here, you may have a decay over here, you may have another one over here, and in fact, you will eventually populate this thing with a tremendously big fractal of different structure like this. What exactly goes on in here? Well, if you have such a sequence of events, you might have another decay from here, and another one, a decay over here, and another one over here, one in here, and so forth. In fact, you inevitably will, at least until you get to a stable vacuum. What kind of stable vacuums are there? Well, for my purposes, I'm going to take our vacuum to be stable. It's not. Our vacuum has a small cosmological constant. We can probably decay out of it, but I'm going to ignore that small cosmological constant for today. We should come back to it. What happens if you decay to a vacuum with vanishing cosmological constant? All right. Let's try to draw the figure that would represent that. Let's suppose that we decayed. Where's my eraser? Yeah. Let's suppose that we decayed from the ancestor vacuum, which is the one just before our own. That's this one over here. I'm not going to draw in the whole sequence of things. Let's suppose, I meant to say, this picture here, of course, is the parallel picture. The parallel picture in which many things go on simultaneously. What's the series picture? The series picture is to pick an observer in the remote future and go backward along his world line and see what he sees. He'll see a series of transitions until he ends up at some kind of vacuum which is, for some reason or another, stable. There are several kinds of stable vacuums. First of all, there are ones with negative cosmological constant. We can't live in those, and we can't even get to them. We can get to vacuums with very, very small or vanishing cosmological constant. They have no more vacuum energy, and they can be stable. Let me draw for you what that looks like. What that looks like, well, here's how we think about it. Let's suppose we actually decayed to empty space with zero cosmological constant. Here's the conformal diagram representing empty space. That's empty space. Here's t equals infinity, t equals minus infinity. I mean flat space now. That's flat space. Okay? We're going to create a bubble in here of something very close to flat space with vanishing cosmological constant. The way you do it is you cut out a region representing the growing bubble, and you replace what's inside by a piece of the flat space. The piece of the flat space is this quarter, or this quadrant up here. So what you get looks like this. This is not the complete flat space, it's just a quadrant of it, the upper quadrant of it over here. Okay, let me tell you what I think the idea of observer complementarity teaches us. It probably teaches us that if we want to do, if we live in here somewheres, and we want to do conventional quantum mechanics, the non-redundant description of quantum mechanics, in my view, does not require us to go beyond the horizon. What is the horizon in this case? Just project light-like lines down like this. Anything out here is beyond our horizon. Anything out here is beyond our horizon. cannot send a signal to us. All kinds of things we might imagine going on there, but in my view, the idea of observer complementarity tells us that it's all contained in a non-redundant way within our own patch. So we shouldn't have to think about the things which are out here. Maybe we want to. There may be good reasons for thinking about it, but we should be able to have a self-contained description of everything within our own horizon. Furthermore, we can take the beginning of the universe, for our purposes, to be this light-like upside-down cone over here. Of course, that doesn't mean that things can't come in from the outside, but we can think of those as initial conditions on our initial surface over here. So, from that point of view then, the whole world can be thought of as taking place in this diamond. Nothing out here can affect us. Anything out here can be represented as part of the initial data on this backward light cone here, and all of the world, from our point of view, is simply contained within this diamond. So the question is, what kind of cosmology is contained within that diamond? Any questions at the moment? Okay, the answer for the kind of cosmology that's in here is that it's Friedman, Robertson, Walker with negative curvature and infinite spatial extent. So let's see how we can see that. Imagine foliating this diamond in here with a series of curves that look like this. The metric up in these corners here, divergence, it inherits the divergence from the infinity in the metric as you go up to time like infinity in de Sitter space. So the metric is quite infinite at these corners over here, and the total spatial extension along one of these space-like surfaces is infinite. Most of it, of course, is in these corners here. Okay. That's one statement. When we study the Coleman-DeLucia instanton, which is the mathematical description of this decay, what we find is that the surfaces on which physics is homogeneous, in other words, the surfaces on which physics is the same from point to spatial point, is just this kind of set of surfaces here. They form a very particular set of surfaces. They're hyperboloids, or they have the character of hyperboloids. And even more, these surfaces are exactly the same as the diagram which has now disappeared off here. They are the hyperbolic plane, or the Escher drawing, or Euclidean anti-de Sitter space. So when you create a bubble, you create a universe, even though it looks like it's contained within a finite region, that universe is, for all your purposes inside here, infinite, open, Friedman, Robertson, Walker, I'll write the metric for it in a moment, and it consists of a series of layers of time-like slices, no, space-like slices, each of which has exactly the structure of an anti-de Sitter space, or a Euclidean anti-de Sitter space. Let me write down the metric that describes this diamond. This diamond, it is just FRW. ds squared is equal to minus dt squared. We can slice this up so that we also see some co-moving coordinates. Co-moving coordinates would look like this. Incidentally, the scale factor vanishes right at this point. That's where the FRW universe has its big bang. In fact, along this whole backward light cone here, the scale factor is 0. The scale factor is constant along these surfaces here. And so the scale factor goes to 0 along a hyperboloid, which sort of sticks to the backward light cone. The metric is ds squared. Can everybody see over here? Yeah. ds squared is minus dt squared. Dt being just measured along these co-moving lines, then plus a scale factor, A of t squared, and I'll tell you what A of t roughly is in a little while, times dH3 squared. Now what is dH3? dH3 is the hyperbolic plane, or the Euclidean anti-de Sitter space in 3 dimensions. And the scale factor just tells you the scale, the overall scale with which that geometry increases. Okay, so it's a series of layers of anti-de Sitter space, growing in scale factor. That's the geometry which comes from bubble nucleation. Let me just write down also what the H3 is, what H moving. All right, so H3, BH3 squared is just the r squared, where r is proper distance along the surface here, a radial coordinate, plus sinh of r squared times d omega 2 squared, where this is a 2-sphere. So you look out around you, you see a series of concentric 2 spheres, each one at radius r, but the radii of the 2 spheres grows exponentially. That's Euclidean anti-de Sitter space. That, I think, to my mind, this is the cosmology which is most suggested by what we know, namely the existence of a landscape, the existence of inflation, the idea that we should stay in our own causal patch and not try to study out things outside our own horizon. And later on, we'll come to what the holographic principle may say. Incidentally, you might have a guess about what the holographic principle would say. No, I won't tell you. I'll let you guess. Okay, now I want to talk about the qualitative properties of such a cosmology. They are not as well known, I think, as they should be. I don't know, maybe they are well known here, but I find generally they're not as well known. Can this thing go up? How do you make it go up?
Control box. And then
Control
desk.
box.
Desk.
Where? Am I going warmer, colder?
Facing your own way.
Facing your own way.
Now go to your left.
Left. Oh, control box. Then what do I do?
Like probably. No, the on the top.
On the top. This thing?
No.
This thing?
Yes.
What do I do?
It should be some button, something that you can put that looks like a stop. Put up the.
No, there's no buttons. Hello?
No, it's touch screen.
Touch screen. Oh, yeah. Home. I don't want to go home. Select video source, lighting presets, local camera, auditorium cam, video controls, audio controls. Oh, it says audio controls.
Yeah.
System shutdown.
We have help coming.
I want to pick up the screen. Okay. Then I'm finished with it. I just wanted the screen to show what anti-de Sitter space looks like. Okay. Let's come back to this cartoon picture of a landscape. Let's call this A for ancestor. Let's call this B for, I don't know, B for Big Bang. B will correspond to this point over here, where the Big Bang takes place. Let's call this an interval over here, between here and here. I'm going to call C, and C stands for curvature dominated. And then the rest of this line here we're going to call SR. SR stands for slow roll inflation, and this we can call N, which means now. Okay? A is the ancestor, B is the Big Bang, C is the curvature dominated time, SR is slow roll, and N is now. Let me show you what they look like, or where these various these epochs, where are they on this diagram? So what do they look like? So here's your FRW universe. spatial slices all pass through these points here. Incidentally, of course, this thing is a higher dimensional version of what I've drawn. All right, there's a time between here and here when, as I said, we'll see what it means, the universe is curvature dominated, and that persists from the Big Bang over here until some point, which I'll call T star, and I'll tell you how it's determined as we get to it. Then it enters a slow roll inflation region. Here's the slow roll, here, slow roll, curvature dominated. I guess we would call this point over here reheating, but all it is the end of slow roll inflation, and then now is up here. A few interesting things happen during what I call now. For example, decoupling, galaxy formation. Galaxy formation might be on some surface about over here. We're over here, looking back at this thing. This is what the universe would look like if it were an open FRW universe that was created by a tunneling event, Now, there's something interesting to notice. The geometry is not singular over here. Well, I'll come back to that. I'll come back to that next time. The geometry is not singular at the point of origin over here. We will come back to that. I'm not going to discuss that right now. But I won't. Next lecture, I'll discuss that. Okay. Okay, what goes on during this period here between the Big Bang and, in particular, the end of inflation? Let me write down the FRW equations and show you, in particular, I want to show you what curvature-dominated region means. The curvature-dominated region, incidentally, these spatial slices are not flat. These spatial slices are negatively curved, just like Escher's drawing. It's during the early epoch here when that curvature is important, when the curvature is more important than anything else, and that's the curvature-dominated region as you come out here. But let's write some equations. All right, so the Friedman-Robertson-Walker equations are A dot over A squared, where A is the usual FRW scale factor. Well, what is it, 8 pi g over 3. That's not important. And then there's some scalar field, the inflaton field. The inflaton field is rolling down the hill. We have a phi dot squared, this is just energy density, plus V of phi, where V of phi is this potential. And this is all you would have. Of course, there may be other sources of matter, other sources of energy, but the dominant source of energy as you come out from here would be the inflaton. This would be all you would have in flat FRW. In negative curved FRW, you have another term, which is 1 over A squared. Positive 1 over A squared. When A is small, A is 0 on here, here, and at the tip. When A is small, this is the dominant contribution to cosmology. It's the most important thing. Until a particular point. Incidentally, slow roll usually means that this is not so important. Phi dot is not important. V of phi is important. The point at which slow roll goes over, the point at which curvature dominated, that's when this is the most important thing, goes over to slow roll, is the point at which the 1 over A squared is comparable to V of phi. So we'll estimate that point in a minute. But I want to tell you what some of the possible important aspects of the negative curvature-dominated time are. They solve some problems, the negative curvature. Yeah.
In drawing your Ferrell's diagram, you have assumed that from tunneling from your ancestor vacuum, current vacuum,
yeah.
the cosmological constant in current vacuum is 0. But
Yeah,
you want to
I have assumed that in drawing this figure, yeah.
but then you want to apply it to our universe.
Yeah.
So
Okay, so
inflation happens to the non-zero cosmological constant.
in here, yeah. Well, okay, but that's just rolling down the hill here. That's rolling down the hill here. So in here, you have a piece of what looks like the Sitter space until it ends over here. You could ask, supposing it didn't end, supposing you actually just ended up in the Sitter space, what would it look like? All right, it would just terminate. It would terminate a little bit higher than this, terminate over here someplace. Terminating on another space-like infinity, on another space-like time infinity. In de Sitter space, time equals infinity is a space-like surface. If you want to take into account the fact that our now vacuum actually has a cosmological constant, then what you would actually draw would be almost exactly like this because of the smallness of the cosmological constant, but it would actually be space-like and would look like that. Okay? In practice, it would be very, very close to being light-like, and if we make the approximation that our cosmological constant is 0, there's no particular reason to do so. I just wanted to be simple about it and not worry about it. Then we would just draw the light cone. If we want to take into account that there is a late time cosmological constant, then this surface just gets a little bit bent like that. And the end of time here would be a place where the exponential divergence in the metric blows up.
What if you want to say things like contrast, you have inflation? How should
That's in here. The scale factor in here is doing whatever the scale factor does. All we have to do is solve these equations. So we would solve these equations, for example, with just a lambda here. Forget this, just put a lambda in and solve these equations. What will happen is at some point, the vacuum energy will become bigger than 1 over a squared. Okay? At that point, you will start to have an exponential expansion in here. That's where you'll have an exponential. So exponential expansion will be taking place in here. This is just a causal diagram. This diagram is not the metrically faithful diagram. The scale factor is increasing according to some rule, which is determined by this equation. The fact that it's negatively curved and has a causal structure like this is represented by this. So, right, everything is in this equation. There's another equation. There's an equation for the matter field, which is, or the inflaton, which is 5 dot squared, oh sorry, 5 double dot, plus 3a dot over a times 5 dot is equal to minus dv by d phi, where dv by d phi is just whatever dv by d phi is. This is the second equation. All right, so let me tell you, first of all, one of the things that the negative curve, we can immediately estimate where this boundary is between the curvature dominated and the slow roll is. That is when 1 over a squared becomes about as small as v. V on this plateau, for phenomenological reasons, is about smaller than. I'm going to take it to be roughly equal to, but this is not important. It's smaller than 10 to the minus 14. That's how big V is allowed to be without violating things that we know about cosmology during slow roll inflation. When that becomes equal to 1 over a squared, in other words, when a increases to the point where it crosses over the vacuum energy here, 1 over a squared, that corresponds to the point where you go from C to SR. I should tell you one more thing. If you solve these equations in the curvature dominated situation, where this is much smaller than 1 over a squared, you find that a is just equal to t. That's a solution of this. A dot over a squared, supposing a is equal to t. Then a dot is equal to 1. A dot over a is 1 over t. This is 1 over t squared. This is 1 over t squared. So A equals T is the solution of the curvature-dominated universe. And so we find out that this transition point, T star, occurs at about 10 to the 7th or later. About 10 to the 7th in Planck units. So about 10 to the 7th, at least 10 to the 7th units of time you're spent in this curvature-dominated era. Now, what is the negative curvature good for? Well, it does solve a problem which various different people have various different views about how serious it is. I call it the overshoot problem. It's slightly different than what is sometimes called the overshoot problem, but I think this is the place to think about it. Remember, this height here is very, very small. It's practically zero. We don't know anything about this vacuum, but the cosmological constant in this vacuum could be quite large. When you tunnel through here, you're going to be falling down rather rapidly. What's to prevent you from just overshooting this point? Now, if you take some standard numbers, of course, if you start on this very slow roll plateau, and you start slow rolling, nothing much happens to you. You just slow roll. But supposing you start high up on this edge over here, and you start rolling down, what's to stop you from just overshooting completely? Well, the thing that stops you is this cosmic friction term here. That's the thing which can potentially stop you from overshooting. But if you put in the cosmic friction term as it would be in flat space, you'll just overrun completely. It's this term here. Well, let's see, what is it? It's the fact that in negative curved space, A dot over A is 1 over T, which gets very big at early times. At very big at early times, the cosmic friction here is huge. In fact, the cosmic friction is much larger than it would be during the slow roll inflation, because the slow roll inflation doesn't happen until T star is about 10 to the 7th. So during this period, which is what I call the curvature-dominated time, there's an enormous amount of cosmic friction on the inflaton. In fact, it diverges at T equals 0, and simply stops the motion dead, practically dead. It doesn't roll very far, no matter how high it starts from, and no matter how steep it falls, it just doesn't get very far. That's easy to check. I won't do the numerics of it for you, but it just doesn't roll very far because of this large amount of cosmic friction. So the negative curvature, which gives you A growing or shrinking like T as you go toward the early times, provides the only, as far as I know, the only real known mechanism to prevent you from overshooting here if you start up high. That's the main reason that I focused on this region.
What happens if we end up in a closed universe?
What happens at the end of what?
The friction term is proportional to what?
Say it again.
If we end up in a closed universe, what happens to the friction?
You can't end up in a closed universe. There's no way that this can end up in a closed universe. Bubble nucleation just will not end you up in a closed universe. Point is, how could you end up in a closed universe? Here we are, we have this. We get stuck in a minimum, a metastable minimum. If the minimum is reasonably stable, you will inflate many, many, many times before you decay. So the universe grows to enormous proportions. It cannot simultaneously everywhere decay. That's not the kind of thing that can happen to a metastable vacuum. It'll decay in bubbles. If it decays in bubbles, this is what you get. That's the whole point. Forget, if you have any confidence at all in the idea of a landscape and the idea of starting up high on the landscape and evolving your way down, then you might as well forget the closed universe. You cannot get to it. You simply can't get to it. That's probably the most important message.
Because if it's closed universe, I think the gain, the curvature, the friction terms the gain proportional to 1 over t, and the same argument applies.
But you get the opposite sign here. You get the opposite sign. You get the opposite sign that let's see, the same argument may apply. I actually never thought about it. Let's see. Probably true. Yeah. Probably true. Yeah. Right. The point may not be negative curvature. The point may be curvature. A lot of curvature. I'm not sure. I have to think about that. Whether positive curvature would do the same thing. Not sure. Let's see. Wait a minute. No. It can't make sense. You can't ignore this term for positive curvature. For positive curvature, if this term weren't there, you can't solve the equations. It's just no solution. A dot over a squared is equal to minus 1 over a squared. It's inconsistent. It's got to be dominated by matter. It can't be dominated by curvature for positive curvature. It can only be dominated by curvature for negative curvature. All right, let me tell you a little more about the transition between curvature dominated and non-curvature dominated or vacuum dominated. Let's see, who's in charge here?
Okay, let's see.
What time should it be?
Well, usually it's an hour, so you can go maybe for 10, 15 minutes.
All right, however you want. I'm happy to stop whenever you want. Let's follow as we go from the. Oh, there are 2 other points here that I neglected to say. Well, I did say one of them. I did say that in the early times here, that A is proportional to T. And that's a true statement. A is proportional to T. So that's a boundary condition on A at the very early times. There's another boundary condition that follows from something that we haven't done yet, which is the Coleman-DeLucia instanton, which describes this evolution, or describes this bubble nucleation. It is the statement that at A equals 0, when you come out at point B here, at Big Bang, when you come out onto the Big Bang over here, that's A equals 0, you come out with phi dot equals 0. Phi at rest. Phi dot equals 0 at this point over here. So you start from rest. If you were to look at phi at this point and go upward, phi dot would be 0 at that point. That's a consequence of tunneling. That's a consequence of standard tunneling. You'll always come out from the tunneling event at rest. We can prove that, but we won't do it now. You come out at rest and you start down the hill. So you have a complete set of initial conditions, A growing like time from this point, and phi at rest at this point, and just evolving under the influence of a good deal of cosmic friction. Now, let me show you what the Hubble horizon looks like. The Hubble horizon would look something like this. Now, what is the Hubble horizon, first of all? The Hubble horizon, by definition, or the Hubble length, A dot over A at any given time is called the Hubble constant, right? It is not a constant, so let's just call it Hubble non-constant. It's not a constant, and in fact, during slow roll, it's just equal to 1 over time. During curvature dominated, it's 1 over time. During slow roll, it's almost constant. It's almost exactly constant, the Hubble size. Now, I'm interested in the Hubble horizon size in co-moving coordinates. In co-moving coordinates, you have to multiply this by the scale factor. So the Hubble radius in co-moving coordinates is h times a. A during curvature dominated is just t, and so the Hubble horizon scale during the curvature dominated period is just 1. What does that mean? I'll tell you what it means. It means that the Hubble radius is equal to the radius of curvature of the negative curved hyperbolic space here. A hyperbolic space has a radius of curvature. In co-moving coordinates, that radius of curvature is constant. And this just says that the Hubble horizon is basically one angel or devil big. That's during the curvature-dominated era. So at time, from time t equals 0, for some time, the Hubble radius in co-moving coordinates just stays constant. That stays that way until you move into the slow roll region. Now, with the slow roll region, you basically have de Sitter space. In de Sitter space, the Hubble horizon shrinks exponentially in co-moving coordinates. Everybody know that? Okay, I assume everybody knows it. That in co-moving coordinates, the point is, of course, co-moving coordinates expand enormously rapidly. The Hubble radius stays fixed in de Sitter space, and so in co-moving coordinates, it collapses. Once you get to T star, the Hubble horizon starts to shrink exponentially until reheating. At the time of reheating, it starts to grow again. If you're a cosmologist, you've seen this figure, well, you've seen pieces of this figure before. This is important for the following reason. Fluctuations are produced during the time that the Hubble horizon is shrinking. Those fluctuations, these are cosmic CMB fluctuations. The cosmic CMB fluctuations are produced by coming out of the horizon, so to speak. They're coming out of the horizon, they're being produced, they're frozen, and then they come back into the horizon. During the curvature-dominated era, no fluctuations are produced by the same mechanism. They begin over here. So on sufficiently big scales, basically scales bigger than the radius of curvature of the negative curved space, you produce no fluctuations, at least not by this mechanism. I think I'm going to try to finish up fast. Let's see. That has empirical consequences, but only if the universe has had a sufficiently small amount of inflation, slow roll inflation, that we can have a chance of looking back to this era here. You know, I think I'm going to stop. I'm going to take questions at this point now because we're going to get into too much detail. Perhaps you'll ask the right questions and I'll answer them. Interesting question. Let me just try to give you a few interesting questions. What bizarre and strange logic would have ever created a structure like this? Well, I think the answer is with 10 to the 500 vacuums, almost certainly there will exist structures which look roughly like this. Things not too different have been found in string theory, but it takes a good deal of fine-tuning. The question is, why such a large degree of fine-tuning? So let me qualitatively tell you why I think the fine-tuning for this kind of potential was essential to our own existence. The argument is in parallel with Weinberg's argument about the cosmological constant. Weinberg's argument about the cosmological constant is if the cosmological constant were too big and positive, it would create repulsion. Repulsion would work against galaxy formation. It would prevent galaxy formation from occurring along here. Well, negative curvature does exactly the same thing. Negative curvature, another way of talking about negative curvature from the Newtonian point of view, is that negative curvature means that you're beyond the escape velocity, that the universe is beyond the escape velocity. Being beyond the escape velocity means you've been shot out of a cannon and everything is receding faster than the velocity necessary for stuff to turn around. A small fluctuation, a small fluctuation in the background density will not turn around and form a structure if there's too much negative curvature, because it corresponds to being shot out of a cannon with too much velocity. If you ask, what is it that's going to dilute the negative curvature? It's the slow roll inflation. So you can ask, how much slow roll inflation do you have to have in order that you dilute the curvature, the negative curvature, enough so that galaxies can form? And the answer is almost as much as the empirical bound on the negative curvature. You almost have to have enough e-foldings of slow roll inflation to dilute the curvature. You need almost as many e-foldings as the empirical lower bound on the amount of slow roll inflation. What this translates into is the statement that you need a broad plateau here to dilute curvature during slow roll inflation. Otherwise, you couldn't create structure. So it's my view that the real reason that we have inflation, slow roll inflation, is not to make the universe flat. The universe being flat is a fact. I mean, and there was a lot of slow roll inflation. But why did it have to happen? It's a highly fine-tuned thing to get enough inflation to make the universe as flat as it is. The answer is, if it wasn't as flat as it is, the negative curvature would have prevented galaxy formation, would have prevented structure formation. So, in my view, the reason that we have inflation is because negative curvature would have shot us out of a cannon with much too much velocity to form galaxies. The real interesting questions, which I'll just try to finish up with very quickly, are what are the empirical consequences of negative curvature? The answer is, if there's too much e-foldings during slow roll, the empirical consequences, there are none. It all gets washed out. All the consequences of negative curvature get washed out. If you take the view that it's very difficult to create a large amount of inflation, that we need enough inflation to exist, but perhaps there was not much more than was necessary for our own existence, then you have a chance of looking back to the curvature-dominated era. In other words, the largest structures on the sky could have originated just about at the end of the curvature-dominated era. If that's the case, then there are loads of empirical consequences. The simplest being that you should see negative curvature. Well, we don't see negative curvature. We don't see any curvature. But of course, we don't see any curvature to within some tolerance. And it's not very good. The only thing we know for sure is that the universe is at least 10 times bigger than the radius of radius of curvature is 10 times bigger than the region we can see. We don't know anything beyond that. Future experiments will measure the curvature of space to higher precision. If the curvature of space turns out to be zero, well, it just means there was too much slow roll inflation to see the curvature-dominated region. If it turns out to be negative, I would say it supports this view. If it turns out to be positive, I think it completely falsifies the entire view that comes from tunneling from the landscape. So I would say there are empirical consequences, either flat or negatively curved. Positive curvature, I think, would be a disaster for this view. There are other consequences. One of the most interesting has to do with gravitational waves. The energy density during here is very low. It's not likely to create gravitational waves. So the fluctuations that are created during slow roll inflation do not contain typically a component of gravitational wave radiation. or they do they contain a component of it, but far too small to see. But on the other hand, if we started up here with a very large vacuum energy, many orders of magnitude larger than down here, then gravitational waves were created like mad up in here, and that would mean that gravitational waves from the ancestor vacuum will penetrate into our vacuum. If that's the case, then we should be able to see gravitational radiation, but only on the largest structures on the sky, because they will very quickly get diluted by the slow roll inflation, and only those which are sort of frozen in from very, very early times during the curvature-dominated region here, which would correspond to very, very large things on the sky, would remain. So one potential prediction, or one potential consequence of this view would be that we should see at very, very low L, at very, very large angle on the sky, gravitational radiation, which means tensor modes, which means B modes in the CMB, that very quickly die off as you go to smaller structures on the sky. There's lots of consequences. Lots of consequences. They all depend on the assumption that this plateau is not so broad that it washes out everything that occurred in the early universe here. Okay, I'm going to quit here. If there are any questions, I'll be glad to answer them. If I've completely lost you, so be it. Yeah.
If the universe is negatively charged,
Yeah.
and the plateau is not broad, then at low L's, instead of suppression, we should see amplification of it.
Say it again. Say it again.
At low CMB modes, we should see amplification instead of suppression
Amplification of what?
of the power spectrum.
Of which?
Of the power spectrum.
Of the power spectrum. Power spectrum of what?
Of inflaton.
No, I don't. I think this is delicate. You're saying, supposing this is not very broad, what do you see from coming down here? That's what you're asking?
And if the universe is negatively charged,
Yeah.
then instead of suppression, we should see amplification.
I don't think so.
Uh,
I don't think so. You see, first of all, are you talking about the very low L?
Yeah.
Very low L means very big on the sky.
Yeah.
The biggest on the sky that you can create those fluctuations is out here. So you see nothing beyond that. So I would say from the ordinary mechanisms, I think you won't see anything at very, very large L. Certainly very, very low L. So I would guess a suppression. Now another reason that you might expect a suppression is as you come down off here from here, phi dot will be bigger than it is over here. And remember that the fluctuation spectrum is h squared over phi dot. So it's delicate. It depends on whether h wins or phi dot wins. It is delicate. Depends on the shape here, whether you get amplification or suppression. If phi dot wins, then you get suppression. If h wins, then you get amplification. It depends on the shape of this quadratic curve here. If the quadratic curve is very smooth, then you get enhancement at low L. If it's fairly sharp, then you get suppression. But what you're almost certain to get enhancement of is the tensor modes coming from here. The tensor modes from here are enhanced not because of phi dot, but because of a big H in here. And they just pass through. The reason you don't get scalar modes from in here is because the scalar has a large mass in here. If the scalar has a mass in here, it's not free to fluctuate in there. So you wouldn't expect to get a lot of scalar stuff from in here. But the graviton is massless in here. And so you get a lot of gravitational fluctuation in here from the large expansion rate. And that can penetrate into here. It's then inflated away. It is inflated away by the inflation, but you could see it on the largest modes in the sky if there isn't too much inflation.
Then people observe this low L suppression, George of Stacy was.
Say it again? Oh, well, I seriously doubt that this has anything to do with the low L anomaly. I mean, I don't know, but I wasn't suggesting that it does.
I mean, we should have observed something completely reverse to what we see right now. It's negative here. Because that paper suggests that
Which paper?
that paper by George Susskind, that it says that positive curvature can create this slow suppression. And for negative curvature, for negative curved universe,
Yep.
the Hubble spectrum is increased.
I don't think that's right. I've spoken to George. George never told me that. But if he thinks that, I think he's wrong. Let's see.
But it's not statistically important anyway.
What's that?
It's not statistically important.
I don't think it's statistically important, no. I wouldn't put any money on that low L thing. The thing that might be statistically important, which is part of another story, is the locking of the directionality of the lowest L modes. If there's the directionality of the L equals 2 and the L equals 3 modes seem to define the same plane, as you probably know. Okay, is that significant? Well, how many parameters is that? That's a fairly significant number of parameters. It tells you that both the L equals 2 and the L equals 3 are essentially planar. In other words, that they vary around in a plane, which tells you, in the case of L equals 2, there are 5 polarization states. 3 of them are very small compared to the maximum M. The maximum M equals 2, minus 2, 1, minus 1, and 0. The dominant ones are M equals 2 and minus 2 about some axis. And then the same kind of thing is true of the I was talking about the quadrupole. The same thing is true of the octupole. And so there's a whole bunch of parameters which appear to be locked. Now, if that's true, if that turns out to be true, that seems to me to be statistically pretty significant and requires some kind of explanation. But I would, again, that could easily be statistics also. Or it could be foreground, it could be all kinds of things. An interesting question is how you can create that kind of anisotropy. I'll tell you one way you can create that kind of anisotropy. This has been studied a little bit by Alan Guth and collaborators, but it's never been quantified, never been very well quantified. If you take this picture of a bubble nucleation in de Sitter space, it's absolutely impossible that there be only one and only one isolated bubble, isolated from the others. And the reason is the following. If you follow a track up to this point over here, the proper time along this track is divergent. If there's any non-zero nucleation amplitude for bubbles of whatever kind, there will be bubbles colliding with your bubble. So it's absolutely inevitable in this kind of cosmology that you get clusters of bubbles colliding with your own bubble. These clusters of bubbles lead to anisotropies on the sky. Whether they can be seen or not, again, depends on how much inflation there is, how much they're washed out by inflation. And in principle, these nucleated bubbles here could form a pattern on the sky that would be significantly anisotropic, I think. So Alan has studied that. I studied it a little bit, but there's been no quantitative study of it. So that's, in the real thing, you really do have to worry about other bubbles being nucleated here. And the problem is that there's no bound on how early they can be nucleated. So you can easily have other bubbles bang into your bubble. A good deal of that gets washed out by inflation, so it's not so easy to see. But if there was a minimal amount of inflation, you might be able to see anisotropy on the sky coming from bubble collisions. So that's another direction, yeah.
So from that last point, can I conclude that in this diamond, the edges of the diamond are finite proper distance away?
Because of the bubble collisions.
Well, no, not because of bubble collisions. Ignoring the bubble collisions.
Yeah. No, the edges of this diagram are infinitely far away along these tracks,
In proper distance.
in proper distance. Yeah.
Okay.
Now, metric diverges along here. So these are infinite FRW universes. If there are bubble collisions, the bubble collision could have some sort of domain wall, and then these space-like surfaces would run into something over here, and there might be directions in space along which they're finite. This would create a very, very fractal-looking universe around you. Now that fractal, if you got to see it directly, would be very, very visible as some sort of fractal structure in the sky. And I'm not talking about fractal, I'm talking about large-scale fractal structure. The only thing that would wash it out would be a lot of inflation that would dilute it. So it's conceivable that we could see some degree of that. I have no opinion whatever whether that has anything to do with the anisotropy that's seen in the low multipoles. Right, good. Okay, the lesson is it is worth thinking about open FRW cosmology. It's probably more than worth. It's probably the consequence of some principles which seem fairly robust to me anyway. Good, thank you.